This chapter is about ensemble learning. So we have seen a number of machine learning algorithms such as decision tree, neural net, and instance-based learning. And but so far we focused on a single algorithm. Okay. So in this chapter, instead of single algorithm, we're gonna study a new method called ensemble learning. So in ensemble learning, instead of single algorithm, we use a collection of classifiers. So we have multiple classifiers, and then each classifier make predictions, and then we combine their predictions, which becomes a final output. So that's the basic idea of ensemble learning. So for example, in decision tree, okay, instead of constructing a single decision tree, we may generate 100 different decision tree, okay, and then we have them vote on the best classification for new data. Okay, so each decision tree make a best classification, and then after that we combine the result, okay, and then that result becomes the final output. So that's idea of ensemble learning. This diagram shows the general idea of ensemble learning. So let's say we have a training data, and then this training data is divided into multiple data sets. Okay, let's say we have 10 of them. And then for each data set here, we build a classifier. Okay, so we have a different data set, and now for each data set we have a classifier. So now we have different classifiers. Okay, so again this data set should be different to each other. Okay, so that means these classifiers again is different to each other. Okay, so okay, so and then each classifier make predictions, and then finally we combine the result of these predictions. Okay, so this combined answer is the final output of the ensemble learning. That's how it works in ensemble learning. This picture shows the strengths of using ensemble learning. So let's say we have a data, and these are the class labels of each data, cloudy and sunny. Okay, and then suppose we have 5 different classifiers. Okay, by using ensemble learning. So 5 different classifiers, and each classifier make predictions. So these are predictions from classifier 1. Okay, and these are predictions of classifier 2, etc. Okay, so this is correct, right? And this is wrong. This is correct. This is wrong. So for the classifier 1, he has 1, 2, 3, 4 correct out of 7 data, right? So he got 4 data correct out of 7 data. Okay. And for classifier 2, again he got 4 correct out of 7. Okay, and then let's say for this one has 1, 2, 3, 4, 5, 1 correct out of 7. Okay, so if you look at the accuracy of each classifier, the accuracy of first classifier is 4 out of 7, 4 out of 7. This one 4 out of 7. This one is 5 out of 7, etc. Okay, so if you look at accuracy of each classifier, the accuracy of these classifiers are actually not very impressive. Okay, the accuracy is less than 70%, which is not good. Okay, but if you combine them, combine the result of each classifier and use majority voting, then for this data, the majority is cloudy, right? So the answer is cloudy. For this one, the majority is sunny, right? So we have 3 sunny, 2 cloudy. So the final answer is sunny. So here again, the majority is sunny and majority is cloudy, etc. Okay, so by combining the result, the final answer is actually exactly same as the original answer, right? So even though the accuracy of each classifier is not good, okay, actually their accuracy is less than 70% or something, okay, which is not impressive at all. But even though their individual accuracy is not good, by combining them, we have very nice, okay, excellent performance. In this case, is 100% accuracy, right? So that's the strengths of ensemble learning. So we have multiple classifiers in ensemble learning, and actually there are some conditions for the classifiers in ensemble learning to satisfy. The first condition is each classifier should be independent to each other. Okay, and then second condition says each classifier should be more accurate than random guessing. Okay, so the first condition is about the diversity of classifier, and the second condition is about the intelligence of the classifiers. Okay, and this second condition is pretty easy. Okay, to be implemented, right? If you pick any arbitrary classification algorithm in machine learning, then probably its accuracy is better than random guessing. So this second condition is very easy to satisfy. So what matter is the first one. Okay, so in the first condition, you should make an effort to make sure each classifier is independent to each other. Okay, so that's why this first condition is important. So diversity is more important than intelligence. Okay, because intelligence is very easy to be implemented. Okay. So when there are a certain amount of diversity in ensemble learning, okay, then suppose you have a multiple classifier and each of them is independent. Then suppose one classifier creates an error. Okay, then it is quite possible then there is another independent classifier which cancels out this error. Okay. So that's why this diversity is important. On the other hand, if the classifiers in the ensemble learning are homogeneous or very similar to each other, then yes, suppose one classifier creates an error, then there is another similar classifier, and it probably generates similar error. Okay. So that way, actually, if these classifiers are homogeneous, they actually amplify errors instead of canceling out the errors. Okay, so that's why this diversity is more important in the ensemble learning. So as I said, diversity is the key factor in ensemble learning. Okay, And actually, it is not limited in machine learning. It is also true in every human decision making, in human as well. This is a very important, actually, property in a group decision. Let's see how the ensemble method works. Suppose we have 25 base classifiers, and assume for each classifier, its error rate is 35%. Okay, and also assume each classifier is independent. Okay, again, I said this is very important. And also assume we're gonna use majority vote when combining the predictions from different classifiers. And then let's compute the probability that the ensemble method makes a wrong prediction. Okay. So because we have 25 classifiers, okay, to make wrong predictions, then the number of wrong answers should be at least 13, right? So let's say I is the number of wrong answer, then I varies from 13 to 25, right? And this E is the error probability, and this error happens I times, okay? And 1 minus E is the correct answer, and the correct answer happens 25 minus I times, okay? And then the number of combinations of this is given as 25 combination I, okay? So put this all together, the probability is 0.06, so it's 6%. So originally the error was 35%, and then by combining these 25 independent classifier, the final error of ensemble method is now 6%. Okay, so we can see a drastic change of error rate from 35% to 6%. So that is the beauty of ensemble learning. So actually, this ensemble mechanism works not only in machine learning, but also works in human ensemble as well. So these are the famous social experiments, and how many, let's say, how many jelly beans in the jar. So there are many people, and they take a guess of how many jelly beans in a jar. Then even though no one gets the correct answer, then if you compute the average value of the estimate, the average turns out to be very close to the actual value. Okay. And another example is in TV show Who Wants to Be Millionaire. Okay. And the case of audience vote, actually this has much more accurate than the case of asking help from expert or friends. Okay, so this ensemble method works in machine learning and as well as the human ensemble as well. So remember, this independence is very important, and the ensemble with similar classifier is actually worse than a single classifier. So diversity is the most important thing in ensemble method. Let's take a look at another example of ensemble learning. Again, suppose we use majority vote, and suppose we have 5 completely independent classifiers. And again, as I said, this independence is very, very important in ensemble learning. So we have 5 completely independent classifiers. And suppose that the accuracy of each classifier is 70%. Okay, then for the final prediction of ensemble method to be true, then at least 3 of them should be correct, right? So this case is where every classifier is correct. Okay, 5 of them is correct. So in this case, four of them is correct and 1 of them is wrong. And this is the case where 3 of them is correct and 2 of them is wrong. Okay. And here in this case, this is the combination of these cases, and this is combination of these cases. Okay, so put this all together, we have the probability of this is 83.7%. Okay, so even though the accuracy of individual classifier is 70, by combining 5 of them, okay, then the accuracy now becomes 83.7%. Okay, so if you keep adding more and you want to add like you want to have like 101 again independent classifiers, okay, and this accuracy now jumped to 99.9%. Okay, so even though the individual accuracy is 70, by combining 101 completely independent classifiers, accuracy now jumped to the 99.9%, which is super excellent, right? So that is the beauty of ensemble method. This one is a definition of binomial distribution, and these values are derived from using this distribution formula. So there are different ways for constructing ensembles. The first method is using different training data. And the second method is using different learning algorithms. Okay, and here in this chapter, we're going to focus on the first method using different training data. And another variation is it depends on the way we combine the decisions of multiple classifiers. Okay, so when each classifier make predictions, you can use either majority voting or weighted voting to combine the decisions from multiple classifiers. So as you can see, there are many variations of ensemble method. This slide shows the second approach in the previous slide, which is using different learning algorithms. So given data, we collect multiple different learning algorithms. For example, KNN, naive Bayes, SBM, or decision tree, right? So given a single data, we have multiple different learning algorithms, okay? And then each algorithm make predictions, and by combining these, we have final predictions. That's how it works in ensemble method using different learning algorithms. So we use different learning algorithms, and sometimes we can use algorithms with different choice for parameters. So in this case, let's say we use a decision tree for all of these classifiers, but with different parameters. Okay, so all these classifiers, all these classifiers are decision tree with different parameters. Okay, so you can implement this method by using same algorithm with different parameters. Okay. We have seen the definition of ensemble with different learners or different algorithms. There is a variation of ensemble with different learners, which is called stacking ensemble method. In traditional ensemble with different learners, we have data and we have multiple classifiers, and each classifier make predictions like this, okay? And then by combining these predictions, we make final predictions. That's how it works in traditional ensemble with different learners. But in a stacking method, we have another algorithm, another learner called level 2 model, okay? And then these prediction values, these predictions made by each of these classifier is now used as a feature of input data, okay? So the prediction value here is now used as a feature of data, okay? And this level 2 model read this data, okay? And then based on this data, it make final predictions. Okay, so that's how it works in stacking ensemble method. So we have two level of algorithms. We have a multiple level 1 algorithms. So in level 1, we have a multiple learners algorithms here. But in level 2, we have only one algorithm, which actually takes the feature values as an input and make final predictions. Okay, so that's the difference. So these predictions from level 1 are used as features to train a level 2 model. So simply put, the combining method of prediction values in ensemble with different learners is replaced by another classification algorithm. Okay, that's the difference between different learners and the stacking method. The previous slide explains the ensemble method, which uses different learning algorithms. Okay, and here this one explains another ensemble method which uses different training data. Okay, and actually this is the main focus of this chapter. So in this approach, we use a single learning algorithm, okay? But actually we manipulate training data and generate multiple training data. So originally we have one training data, okay? And then by manipulating this original training data, we generate multiple training data. Let's say data 1, data 2, or data m, okay? So given one training data, we create m different training data. And for each training data, okay, we construct an algorithm, okay, using this learning algorithm, we create a learner or classifier by using this training data, okay. So by using data 1, we have classifier 1. By using data 2, we have classifier 2. So we have a classifier m. So now we have m different classifiers, okay. So this is the basic idea of ensemble method with the different training data, okay. Then the next question is, here I said from original data, we generate multiple training data, right? The next question is, how do we generate multiple training data from one original data? Okay, that's the main question, main focus of this method. Okay, we're gonna study two methods here. Okay, we have two different methods for changing training data. Okay, so this means from original single data, training data, how do we generate multiple training data like this? Okay. The first method is bagging method, and second method is boosting method. Okay, so in bagging method, we resample training data every time. So we have original data, then we do sampling for the first case. We do another sampling here. So we do sampling m times here. Okay, that's bagging. And in boosting, when you do sampling, we recompute the weight of each training data. Each training data in this case has its own weight, okay? And every time we sample and we recompute the weight value of training data, okay? That's how it works in boosting. We're going to explain this mechanism of bagging and boosting in detail, okay, later on. So how do we generate an ensemble of classifiers? And in previous slide, I said we first generate different training data, and then from each training data, we create different classifiers, right? That's how it works in this ensemble method. So the best basic question now is how to generate an ensemble of classifiers with high independence. Okay, as I said, in ensemble method, each classifier should be independent to each other, right? So how do we create an ensemble of classifier with high independency? Okay. So in this chapter, we're gonna cover these three methods, these three ensemble method: the bagging method, and the boosting method, and the random forest. Okay. The first ensemble method we're gonna study is a bagging method. Bagging stands for bootstrap aggregating, and this bagging method is quite simple, and I'm going to explain it in this slide. So suppose you have a training sample S. Okay, so S is the training sample. Then you generate a sample T from training data S. Okay, and the data in S may not appear in T or may appear more than once. So that means when you generate data T from S, you do sampling with replacement. Okay, so some data in S may not appear in sample T, or it may appear multiple times in sample T. Okay, so that's how you do sampling here, and you repeat this sampling procedure, okay, multiple times. So let's say you do sampling m times, then you want to have m independent sampling of training data, right? So now you have m training data, which is a sample of original training data. Okay, so now you have m training data. So for each of these m training set, okay, you construct classifier C1, C2, Cm, because you have m samples, you're gonna have m classifiers, okay? So when you build this classifier, make sure you use the same classification algorithm, okay? Suppose you use decision tree, then you use the same decision tree algorithm to construct this classifier for each of these m training data, okay? So now you have m classifier, okay, and then let's say you have new data, unknown test data x. Then to classify it, okay, let each classifier here predict or vote. So each classifier here make predictions on the data x, okay, and then finally you combine the predictions of each classifier. Let's say it is C star. So that is C star is just the it counts the vote, and the value of X is the class with the most vote. So simply you choose the majority voting, okay, and the class level with the most vote is the winner, okay. So that's how it works in bagging method. This shows the pseudocode of a bagging method. Suppose you have a training data S of size n, and then for I equals 1 to m, that means you generate m different training data set. Okay, so you draw a sample of size n star, which is less than n from original data here. And make sure you sample uniformly and with replacement. Okay, so with replacement means uh, one data in S may not appear here in the sample, and one data in S may appear multiple times in this sample. Okay, and uniformly means each data in S has the same probability of being selected. Okay, so when you draw sample, you draw a sample of size n star uniformly and with replacement. Okay, so now you have m different samples. Then you build classifier Ci for each sample. Okay, so now you have m different classifier. So for a new data, then each classifier make prediction, okay, and each classifier make predictions, and finally, the final prediction is the most bold from each of the classifier, okay. Let's see an example of applying a bagging method. Suppose we have original data like this. It has 10 data. And if you apply bagging, this is the first round bagging, and the result goes like this. And as you can see here, we have 3 tens and we have 2 fives, okay? And also we don't see 1 here, okay? So because in bagging, we do sampling with replacement. That means some data may appear multiple times like this, or some data may not appear in the sample, like 1 here, okay? So that's the sampling with replacement, and the bagging uses sampling with replacement. So this is the result of round 1 sampling, and in a similar way, we do another bagging sampling around 2, and this is the result, okay? And the round 3, this is another result, okay? So now we have 3 samples, okay, using bagging, and you can create as many samples as you want, okay? So in this example, we have 3 samples. And then for each sample, for each training data here, you're gonna build a classifier, okay? So you can choose any classification algorithm you want, okay? You can use decision tree or neural net or instance-based learning or deep learning, whatever, okay? So that's fine, okay? Whatever you choose, that's simply fine, okay? So for you build a classifier on each sample here, and again, it doesn't matter what kind of classification algorithm you choose, okay? And then, by the way, each sample here, each sample has the probability 1 minus 1 minus 1 over n to the power of n of being selected. So the probability that a certain data here is to be selected is this, okay? And if n is very big, like infinite, this value becomes 63%, okay? Because if n is infinite, this is reduced to this, and which is nearly around 63%, okay? So if n is very big, each data has the probability of 63% of being selected. Okay. All right. We have now we have 3 samples, and we're gonna build a classifier for each sample. So in this example, we're gonna for the classifier, we're gonna use decision stump. Decision stump is a single level decision tree, and this is the one of the most simple classification method. Okay, so for the sake of example, we choose the most simple, the simplest classification method called decision stump. So decision stump is very simple. It goes like this: if a certain attribute x1 is less than a certain value v11, okay, then its class value is C1, otherwise C2. Okay, so that's the decision stump. So you're going to use this one, okay, and you're going to use this one along with these samples, okay, and see how the bagging method works using these examples. So this one shows the detailed example of using bagging. So again, let's say we have original data which look like this. X is input data, input feature, and Y is the class label. Okay, it's a binary 1 or -1. Okay, so if X is 0.1, class value is 1, or if X is 0.7, class value Y is -1. Okay, etc. etc. Okay. So we do bagging, okay, that means we generate multiple samples. Okay, so in round one, you generate a sample, bagging sample in round one, okay. So let's say this is the result of sampling. So we have 10 data, okay, and the result goes like 0.1, 0.2, and etc. So you see here, 0.2 appears twice, okay, and actually 0.4 appears twice, and let's say this 0.7 never made here. Okay, so anyway, this is the first sample using bagging, and this is another bagging sample, round 2, and this is the result of second sample. And a similar way, we have round 3, round 4. Okay, so in bagging, for each sample here, we create classifier. Okay, so in this particular case, I said we're gonna use a decision tree, which is this is the simplest classification method. Okay, so we're gonna use decision stump here. So in this decision stump, it goes like this. In decision stump, let's say you draw a line here, okay, and if x value is less than this line, then we say class value y is 1, okay. And the decision stump also says if x value is greater than this, then y value is, class value y is -1, okay. That's what decision stump says. Okay. So in this case, you draw a line here. If decision stump is defined like this, x is less than or equal to 0.35, draw a line here. Y value is 1. Okay. If x is over 0.35, then class value is -1, right? So as you can see here, there is error. These two data is error, right? This is no error. Okay, and this is no error, but these two are error. Okay, but anyway, it's so for the case of this particular decision stump, its error is 2 out of 10. Okay, so accuracy is 80%, its error is 20%. Let's move on. We have a second round sample here, and if you build a decision stump, the decision stump will be like this. You draw a line here, and it says if x value is less than 0.05, line here, then y value is -1. Okay, and if decision stump x is over 0.05, then y value is 1. Okay. So that's what this decision stump says. So in this decision stump, let's say decision stump says every value, if x is over this line, y value is 1, right? So 1, 1, 1. So this is error. So these two are error, right? So in a similar way, in round 3, this is a sample of round 3, and if you draw a decision stump, this will be the best decision stump. It says if x is less than this, class value is 1, otherwise class value is -1, so these two are errors. So same thing, you have another sample, and the best decision stump is like this, and it says x is less than this, class is 1. For here, class value is -1. Okay. I'm going to continue in the next slide. Okay. So this example continues from previous slide, and now we have round 5, round 6, all the way to round 10. So in round 5, and we have this sample, and we draw a decision stump like this, and every x value less than this is class value is 1. For every x value greater than this, then its y value is -1. Okay, so in this case these three are error, etc. Okay, so for round 6, this is the decision stump. Everything here is -1, everything here is 1. Okay, and round 3, this is decision stump. Round 8, round 9, round 10. Okay, so far we have 10 different samples, and for each sample we build a classifier called classifier of decision stump. Okay, so now we have 10 different classifiers using 10 different training sample, right? And this shows the final result of applying a bagging method. So originally we have 10 data, okay, from x equals 0.1 to x equals 1.0. And this one here is their corresponding class value. So this is the true class value. In round 1, using the decision stump from round 1, this is the prediction, okay, from the decision stump of round 1, okay, and this is round 2, and this is the prediction from the decision stump from round 2. Again, this is the prediction from decision stump 3, decision stump 4, etc. Okay, so we have 10 different classifiers, 10 different decision stump. Okay, and then you combine them. When you combine, we simply use majority voting, okay, because we have +1, -1. We simply add them together, okay. If the value is positive, the result prediction is 1, otherwise -1, right? So if we add this together, 10, the prediction of 10 different classifier decision stump, the summation is 2. That means the final prediction is 1. Okay. And in this case, if you add these together, summation is 2, which means the final prediction is 1. In this case, if you add together, summation is -6, which means final prediction is -1. So in a similar way, this is -1, -1. This one here, summation is 2, which means final prediction is 1, etc. Okay. So this is the final prediction by combining these results. Okay, so this is the final prediction by using bagging method. Okay, so if you compare the result, this result with the true values, okay, then there is exact match. So the final prediction from a bagging method is exactly same as the original class values. Okay. So that's the beauty of bagging. And if you look at the accuracy of each classifier, actually it's not very impressive. For the case of decision stump 1, we have error here, right? So this is error, this is error. So in this case, for round 2, decision stump 2, let's say 1, 2, 3, 4. This 4 is error, okay? So in this case, in round 1, decision stump 1, its accuracy is 80%. In this case, these 4 are error. So in round 2, the accuracy is actually 60%, okay? So the accuracy of each classifier, each individual classifier is not very impressive, but when you combine them by using bagging, their final prediction is very accurate. Actually, in this case, the final prediction is exactly same as the original class values. Okay, so that's the beauty of using a bagging method.